Now, I consider this probably the most important thing in chemistry because it basically tells you if reactions are going to work or not, and it's quite simplistic and how the whole thing works, really. So basically, if it's negative, a reaction works, and if it's positive, a reaction doesn't work. It's that simple. What could be more important than knowing if reactions are going to work or not? And it's just a simple equation. So we've talked conceptually already in standard level what entropy is, and it's got to increase is favorable, and the enthalpy decreasing is favorable, and that makes this more negative, and that makes this more negative. So surprise, surprise, the Gibbs free energy negative, it works. If it's positive, it doesn't work. So elements in the standard states are 0. They're not going to do anything. They're just sitting there. Okay, so just a summary once again. So enthalpy, loss of chemical energy. So you want that to be negative. Increase in randomness, so the spread out of energy and matter, because really kinetic energy is spread by matter. And then so that gives you an overall delta G is negative if it's all favorable. This is the one we need to focus on. Now, the textbook has like 8, and I like to keep it just as this one. It's nice and simple. So the one that we've looked at so far is always this one, the always, everything's the way it should be to work. And so we're losing chemical energy and it's getting more random. Now, if we make it complete opposite, it's never going to work, okay? So it's getting less random and it's gaining energy. That's never going to work unless you're biology. All right, so life has some sort of supernatural component to it. Supernatural beginning, supernatural existence, perhaps. So it completely violates science. But we have those reactions, but in biology. But if it's not life, it's not going to work. And we're not doing biology, okay? So positive enthalpy, increase in chemical energy, negative entropy. So the photosynthesis reaction will never work if we just get carbon dioxide and water and just let it sit there. But if you put them inside a living cell, it will actually turn it into what it's not meant to do. Okay, now the ones that we need to focus on then, because hopefully these two are locked away, are the ones that actually changed varying on temperature. And the key to that is understanding that entropy, if you increase the temperature, that has a massive, massive effect on entropy. Remember, solids and liquids to a gas, there is a huge increase in entropy there. And vice versa. And so we're using temperatures having a huge effect on the entropy. And so if you have a various combinations, so you're gaining heat here, which is not what you want to do. So you're gaining chemical energy and you're gaining entropy. Now that is going to work as long as the temperature is high, because if the temperature is high, that will make this value large and it will take out this positive value and keep it negative and keep it working. All right, but if this value becomes really low, no matter how big the entropy is, I guess you could take it to 0 Kelvin and just get rid of it altogether, and then it won't work. At some point, this will be positive. Okay, and vice versa here. So if you have, I might rewrite the equation here again because I've written too much over those ones. So again here, this one, delta H is negative is what we want, but we don't want the entropy to be becoming more ordered. Now again, it's the temperature that has the critical effect. So at very, very low temperatures, so this negative and this negative means it's a positive overall. Okay, so we don't want the entropy to be at a very, very high temperature. If it's a very, very high temperature, this whole thing is going to end up being positive. But if we keep this at a very, very low temperature, this minimizes this positive effect and it keeps the delta H as negative. And so that means the reaction will work. Okay, so for these strange combinations, I would write out the equation and I would analyze what temperature is doing. So if this one here is positive and this one's positive, then what we want is temperature to be very high. Okay, for this to become negative. If they're both negative, then we want temperature to be very, very low, because it's a double negative creating a positive. We want the temperature to be low so this stays negative. Okay, so I wouldn't memorize the ridiculous number of combinations. The formulas are in the data booklet. Just think through it carefully, and you'll be able to, and hopefully with your understanding of all the concepts, you'll be able to explain all the different combinations. All right, so we're just going to go through actual calculations, which is easier because we just plug the numbers in if it's positive or negative. We don't have to explain or predict. This is much harder to do. And so formation, I'm assuming you'll remember from enthalpy of formation. So we're going from elementals to compounds. So this is the delta G from elements to the compounds. And so therefore this one must get reversed. So it's products minus reactants. So that the F formation is the key to knowing that it's products minus reactants versus reactants minus products for some other things. All right, so products minus reactants, we just need to remember that. It'll probably be nothing else because you only ever get Gibbs formation values. So just plug and play again as we've done all of these. Delta G equals this formula, plug the numbers in. All the numbers it's in, so always formula, substitute, and units. And just a last statement, will it be spontaneous? We haven't actually said it yet. It's positive, so it won't be spontaneous, so it's critical that you do that last sentence. And one last problem, calculate Gibbs for energy change for the combustion of ethanol. So you need the balanced equation for that. All coming back now. So you need to know everything in chemistry. They could ask you anything. So in its standard states, so products minus reactants for this one, not the previous one. So write out all the individual ones, make sure you've got the timesing out, so 2 of that, 3 of that, 0 and 1 of that. Make sure you've looked up the values correctly and put them all in. So formula, general formula, specific formula, substitute, and units. All right, nothing less than that. Okay, you might be able to leave this one out, but certainly not the balanced equation and these 4 lines. Okay, so go have some practice with that.